This is the 43rd lecture, and we are going to, we started this discussion on Cascode configuration. We are going to look at this along with that bag of tricks in a little more details. We are going to look at the Cascode configuration as a wideband amplifier, and the circuit for a Cascode is one transistor sitting upon another, Q1. We are not showing the bias connections, and Q2. This is a common base connection and this is a common emitter connection. The load is in the collector of Q2 RL, and this is V0. The input is at the base of Q1, this is Vs. And in addition, you might have to consider the effect of the equivalent base biasing resistance. This is the configuration, and as I told you, this is available as a chip. This is available as a chip. You connect things outside to make it into a wideband amplifier. The equivalent circuit using the hybrid pi model we had drawn the previous day, and then we had applied some tricks. Let us look at this equivalent circuit again. If we proceed carefully, step by step, this is a fairly involved equivalent circuit. We have Vs, Rs, then Rb, and then for Q1 we can take care of Rx. So let us take Rx into consideration, Rx1, then R pi 1, C pi 1, and this voltage we call as V pi 1 plus minus. Then we have the C mu 1 and GM1 V pi 1. We can also take care of R01 here, okay. The collector, dynamic resistance of the collector, R01, and this is E2, the emitter 2, which has now the following connections. Emitter 2 to ground, you have R pi 2 and C pi 2. This is connected to ground. This is the what is this point? B2. Okay. Then B2, we also have a C mu 2 from the collector 2 to B2, C mu 2, and from collector 2 you have the resistance RL to ground, and between collector and emitter you have the current generator. I hope the direction is right, GM2 V pi 2, where V pi 2 is this voltage. One must be careful about the polarity. Polarity is plus down and minus up from the base to emitter. You make a mistake in this and the whole thing goes wrong. Okay, and the simplification that we argued was that since this point is grounded, well, we can forget about this part of the circuit, and since a current generator GM2 V pi 2 comes here to a node whose voltage with respect to ground is V pi 2, we can replace this by a resistance of 1 by GM2. And if I do that, then you see 1 by GM2, R pi 2 and R01, they can be combined into a single resistance. Alright. So let us call this, did we give a name to this resistance? No. Let us call this as RE2, that is effective resistance from emitter 2 to ground. RE2, let us call this as R01 parallel R pi 2 parallel 1 by GM2. Agree? This is one simplification that I have. alright, after considering this current generator as equivalent to a resistance of 1 by GM2 from E2 to ground. And the other simplification is that under that condition the collector circuit C2 simply becomes RL, then C mu 2 collected to ground. Okay, this point we are considering C mu 2 to ground, RL to ground, and then from the collector goes out a current of GM2 V pi 2. I don't care where this current generator goes. All that I know is that this current has to flow through this parallel combination to produce V0. Agreed? I don't care where it goes. This current GM2 V pi 2 multiplied by the parallel combination of this will be equal to V0. That's all that I need. My aim is to find V0 by Vs. The third simplification that we do is to apply Thevenin's theorem to the left of this. Now, if I do this, but in two steps obviously, first across RB, then across R pi 1. All right. If I do this and take account of these two simplifications, then the equivalent circuit becomes as follows. I get a Vs prime in series with Rs prime, and it's very easy to see that Vs prime would be equal to Vs Rb divided by Rs plus Rb. This is the result of the first Thevenin application, and the second one would be multiplied by R pi 1 divided by R pi 1 plus Rx1 plus the equivalent resistance of the first Thevenin step, that is Rs parallel Rb. Agreed. Wonderful. This is Vs prime, and I write it by inspection. I don't look at anything else. Can I also write an expression for Rs prime by inspection? This would be R pi 1 parallel Rx1 plus Rs parallel Rb. Wonderful. Okay, a two step circuit being considered, being written down by inspection. Is the point clear how this comes at as the equivalent resistance? This is the Thevenin equivalent of the first step that comes in series with Rx1, and the whole thing comes in parallel with R pi 1. So this is the first simplification. Then R pi 1 has been absorbed in Rs prime, so I have a C pi 1. The voltage across C pi 1 would still be V pi 1. Agreed. V pi 1. Then I have the C mu 1, and I have an equivalent resistance of Re2. Re2 is the parallel combination of R01, R pi 2 and 1 by GM2. Re2, and then I have C pi 2, and this voltage is V pi 2. The control current source has been taken account of by the resistance 1 by GM2, which was absorbed in Re2. Oh, that should come. Yes, sure. Where is it? Here?
Yes.
Okay.
So that can also be made as 1 by GM.
No. Why not? Because the voltage across it is not V pi 1. If it was, then we would have been very lucky. And unlucky also. Why unlucky? Because then there is no activity in the whole circuit. It will be a passive circuit. If it could be replaced by a simple resistance, where is the active nature of the device? Activity would have been stopped. Okay. So it's not unlucky, it's lucky. GM1 V pi 1, this is what I had omitted, and then we have GM2 V pi 2. This terminal I leave intentionally open. It could be connected to ground, it could be connected anywhere you like, but the fact is that it comes across a C mu 2 and RL to make the output as V0. All right. Now,
shouldn't the polarity of V by 2 be opposite? Yes, sir.
Current
that's right. That's right. Let's not make a mistake. Yes, you are quite right. Gm to V pi 2, and so V0 is minus Gm to V pi 2 multiplied by the parallel combination of this. Okay. Now,
Where does the capacitance C pi 2 go?
C pi 2 is here.
Goes to ground.
C pi 2 goes to ground. C pi 2 is here. Now we make some more simplification. This C mu 1 still bothers us. Okay, C mu 1. If I could take the effect of C mu 1 partly in the input circuit and partly in the intermediate circuit, things would have been wonderful. Now this is facilitated by Miller effect, number one, Miller consideration. Miller consideration is also greatly simplified here because of several reasons. First, you notice that RE2, which is the parallel combination of R01 parallel R pi 2 parallel GM2, 1 by GM2, if beta is large, then this is approximately 1 by GM2, and R01 is a large quantity anyway, therefore RE2 is approximately 1 by GM2. And the parallel combination of RE2 and C pi 2, the parallel combination of RE2 and C pi 2, the equivalent resistance is, well, 1 by GM2, the equivalent of these two is 1 by GM2, which is the approximate value of RE2, divided by 1 plus, yes, J omega
So GM2 plus
C pi 2 by GM2. Agreed? Okay, let's look at this a little more carefully. This expression, equivalent of RE2 and C pi 2. The equivalent impedance of this is 1 by GM2 divided by 1 plus J omega. Do you recognize what this is? GM2 by C pi 2? Omega T. Omega T2. Omega T2. That is the transition frequency of the second transistor. Alright, the gain bandwidth, so called gain bandwidth product. So this is J omega by omega T2. Operation of the wideband amplifier has to be much below the transition frequency, and therefore omega will usually be small compared to omega T2, and this impedance therefore is approximately 1 by GM2. Alright, because omega shall in any case be much less than omega T2. Is the point clear?
So, but what we use a circuit for widebanding. In that case, our frequency will obviously increase.
You see, in the
operation.
we cannot go beyond omega T for gain will be less than 1. Okay. In one case, we did show that the gain bandwidth product is greater than omega T. Two transistors were used, CCC. And what was the logic? The logic was we are not having current amplification. We are having voltage amplification, and in any case, each transistor cannot be operated, no transistor can be operated with a current gain of less than 1. That does not give you an effect. But the overall effect was that we could go beyond FT because we were not considering current ratio. Here also we are not considering current ratio, but usually the operation shall have to be restricted to values less than omega T2. Even if it is not, it doesn't matter, as you shall see. But for a moment, if this total impedance is 1 by GM2, what is the gain? Gain is obviously minus GM1 multiplied by the load, which is 1 over GM2, and since the two transistors, one is sitting upon the other, the collector currents are the same if beta is large, so this is equal to minus 1. In other words, C mu 1 shall reflect to the input side as twice C mu 1, as I had argued earlier. What will it reflect on the output side as? What does it reflect on the output side? In the ordinary case, it reflects as C mu. But the actual formula, if you remember the Miller effect, actual formula would be C mu 1 plus GMRL by GMRL. In general, it is C mu 1 minus gain divided by magnitude of gain. In general, this is the formula. We had derived this while discussing Miller effect. So in this case, therefore, C mu 1 shall be reflected on this side as twice C mu 1. Is the point clear? Because the gain is minus 1, magnitude gain is 1, so C mu 1, 1 plus 1 divided by 1. Therefore, our equivalent circuit simplifies to the following. Vs prime, then Rs prime, whose values we know, and at the input side we shall simply have a capacitance whose value is, yes, C pi 1 plus twice C mu 1. Agree? Then we have GM1 V pi 1, this would be V pi 1, GM1 V pi 1, and this would be in parallel with RE2, which is approximately 1 by GM2, multiplied by the capacitance would now be how much? C pi 2 plus twice C mu 1. And this voltage is V pi 2. Then we have this current generator which goes nowhere, GM to V pi 2, and you have the parallel combination of C mu 2 and RL, and this voltage is V0. Now you see the three parts of the circuit are isolated, and the gain expression could be written down by inspection. What will be the, let's apply now common sense before going to the actual details.
Why should it be 2 C mu 1 parallel plus C pi 2? Shouldn't it be just C pi 2 plus C mu 1? Because once we use a Miller approximation.
That's what I was saying. You see, Miller approximation is C mu reflects as 1 minus gain divided by magnitude gain.
On both the sides? On both the sides.
No. On the input side it is C mu 1 minus gain on the input side. But since the gain is minus 1, the two become equal. On the other hand, if GMRL was much larger compared to 1, then this would be simply C mu. If the gain was much larger compared to 1, then this would have been C mu, not twice C mu. And this would have been C mu 1 plus GMRL.
Considering C by 2 again, once we make seen that it's approximately.
Okay, we want to bring in the elements which control the high frequency response. Polarity of V pi 2 is again wrong. Yes. Thank you. Okay, now let's argue qualitatively. What would be the gain like? V0 by Vs, obviously V0 by Vs would be V0 by Vs prime multiplied by Vs prime by Vs. And you know Vs prime by Vs is a constant quantity. Agree? Depends on Rb, Rs, R pi 1, Rx1 and so on. So this is constant. The frequency response therefore shall be determined by this time constant, this time constant and this time constant. And it is obvious from common sense that the expression for voltage gain would be of the form AV0, which is the midband gain, okay, divided by 3 critical frequencies, 1 plus S by omega 1, 1 plus S by omega 2 and 1 plus s by omega 3. Can you find out AV0 by inspection? By inspection? Yes, of course. It would be minus GM2RL multiplied by GM1RE2, not minus, because of the opposing sign. Then Vs prime comes as V pi 1 comes as Vs prime at midband, alright, and Vs prime by Vs you know, that is a constant. Therefore, the midband gain can be obtained by inspection. You can also find omega 1, omega 2 and omega 3 by inspection. You can also find this. You see, omega 1 would be determined by Rs prime times C pi 1 plus twice C mu 1. Agree? Omega 2 shall be 1 by Re2 multiplied by C pi 2 plus twice C mu 1. And omega 3 would be simply 1 by C mu 2 RL. No analysis is needed. Everything is the form correct? At the midband, this will drop out, this will drop out, this will drop out. So it is AV0. Okay?
Just repeat how you calculated AV0 midband gain.
Oh, midband gain I calculated like this. I looked at this circuit and came from here. At midband, C mu 2 has no effect. So minus GM2 times RL. Then V pi 2 by V pi 1. There is no change of polarity. It is simply GM1 times Re2. And then V pi 1 is simply the same as Vs prime at midband. And I know Vs prime in terms of Vs. The exact expression is the following. Let me write down the expression. AV0 is equal to minus GM1, GM2, RL, RE2, RB divided by RS plus RB. You understand where these terms are coming from? Vs prime by Vs multiplied by R pi 1 plus Rx1 plus Rs parallel RB. That's it. This is AV0, and you can show, you see, GM1 and GM2 are equal, and RE2 is approximately equal to 1 by GM2. Therefore, it simplifies somewhat, minus GM RL multiplied by RB by RS plus RB.
So you destroyed the R by 1 in the numerator.
I did?
R by 1.
Yes, thank you. I did miss out an R by 1. What does that mean? Minus GMRL. Oh, I could combine this. I could make this into a beta. Agreed? Beta RL. Then I don't have to write R pi again. 1 by R pi 1 plus Rx1 plus Rs parallel RB. This is my midband gain. And I have already said what omega 1, omega 2 and omega 3 are. Can I go back to the previous slide? Omega 1, omega 2 and omega 3. Now, a matter of practical sense. You see, omega 2, as I said, is approximately equal to omega T2. And omega 3, the time constant is controlled by RL and C mu 2. C mu 2 is usually a very small capacitance. The time constant here is controlled by Rs prime. What is Rs prime? RB parallel Rs. Is that right? What was Rs prime? That's right. So it's not necessarily a small resistance. Okay. And the capacitance here is C pi 1 plus 2 C mu 1. And therefore, which of these frequencies do you think shall dominate? Omega 1. Obviously, omega 1 would be much less compared to omega 2 and omega 3. Therefore, to a first approximation, omega h is approximately equal to omega 1. In other words, the source end controls the high frequency behavior. Now, if you are fussy, if you say no, my my parameters are such that omega 1, omega 2, omega 3, none of them I can ignore. If that is the consideration, then the problem is not very difficult. You see, my expression is 1 plus s by omega 1, 1 plus s by omega 2, 1 plus s by omega 3. It is not difficult to calculate omega h exactly. If omega 2 and omega 3 are not an order of magnitude higher than omega 1, then what determines omega h? How do you what is the equation? 1 plus, I can write it down by inspection. Look at this. Omega h squared by omega 1 squared multiplied by 1 plus omega h squared by omega 2 squared. If you don't understand, tell me. Multiplied by 1 plus omega h squared by omega 3 squared would be equal to, that is correct. Now, what is the order of this equation? No, it is 3. 3 in omega h squared. Omega h squared is the variable, so it's a cubic equation in omega h squared. Okay, which can be solved analytically, but it is slightly involved. A first approximation from here obviously would be, ignore the terms omega h to the 4 and omega h to the 6. Then if you do that, once again I don't want to do any calculation. Can you tell me by inspection what would be the relationship between omega h and omega 1, omega 2 and omega 3? 1 by omega h squared, that is correct. Omega 2 squared plus 1 by omega 3 squared. And you can see from here that if omega 2 and omega 3 are 10 times omega 1, then omega h is approximately equal to omega 1. Right? If omega 2, 3 are at least not 4, I wanted you to make that mistake. No. You see, you are also squaring this, don't forget this. 10, that's right. Point clear? You see, we are comparing omega 1 squared with omega 2 squared and omega 3 squared. So, omega 1.
So we have to neglect omega 2 squared compared to omega 1 squared.
That's right. So, omega 2 squared, omega 2 by omega 1, that squared has to be greater than 10. You are right. 3.3 is okay. Alright? You know another method of calculating the high frequency 3 dB cutoff. What is that method? The method of open circuit time constant. Now if you do that, what would be the result? Omega h by open circuit time constants. What will be the result on omega h? Pardon me? Summation of? No. It would be 1 by omega h would be 1 by omega 1 plus 1 by omega 2 plus 1 by omega 3. Isn't that right? Time constants add. That means the frequencies, the reciprocals of frequencies add. So you have several approximations. One is this, the other is simply omega 1, and the fourth one is an exact solution of that equation. You can compare and you can see that in a practical case they don't differ much. Any one of them would be good enough in a practical case. We shall take an example in the in the problem session to illustrate this fact. Our next broadbanding technique that we shall discuss is that of using feedback. Broadbanding by feedback. Now, we have discussed feedback earlier and one of the advantages of negative feedback that we pointed out was the increase of bandwidth, broadbanding. Now, in this couple of lectures we shall discuss actual circuits for such feedback, starting with simple ones and then going into more complicated ones. You will see that even analysis of a simple feedback circuit, negative feedback circuit, if you take all the capacitances into account, you must have noticed that while discussing feedback we only considered the midband situation. We didn't consider any frequency response. So now, however, we must meet the truth sometime or other. Let's see how complicated life becomes. Even a simple feedback, you will see how complicated life becomes. Now, feedback can be either local or overall. Local or overall. Local means if you have a single transistor amplifier, you have a feedback local, maybe through a resistance between the collector and the base RF, or maybe through an unbypassed RE. Okay? Both cases will take account of. This is local. Feedback can also be overall. For example, you have a three-stage amplifier and you apply either series or series shunt or shunt or shunt series feedback. Okay? Feedback can also be overall. Usually a circuit designer prefers the local. Can you tell me the reason? Usually a circuit designer does not go to overall feedback unless he has to. Can you tell me the reason?
Gain is affected too much by overall.
It's not gain.
Individual parts can be.
It's easier to analyze and design. Period. Life becomes more simple. And a single feedback, single transistor feedback, it is easier to control its stability. If there are three such, how many capacitors do they introduce? 9 of them. C pi, C mu, C0 for each. 9 of them. And you don't know what will they conspire to. 9 enemies, it is easier to fight 3 rather than 9. Okay? So, overall feedback is used only when it is essential. Local feedback is preferred. And local feedback, we will consider, there can be many types of feedback. We will consider only 2 of these cases. That is, one is a series, one is a shunt feedback. Let me draw this circuit and ask you what kind of architecture it is, rather than telling you what it is. That is, I have a circuit like this. I am only showing the AC equivalent circuit. This is my output, and I have a resistance between here and here. We call this RF. Now, what kind of feedback is this? What is the architecture? Shunt or yes, it is shunt. Okay, shunt. And therefore, if it is shunt, what should be my model of the amplifier? Current to voltage. That's right. Okay. So I will model the source as a current source IS and a resistance RS. RS, if desired, do I require a resistance here between the base and the emitter? No, I don't, because my RF supplies that. Okay. So this is my simple local feedback circuit. And even here you will see how complicated the analysis becomes. Shunt. This is just one example. My equivalent circuit becomes IS, RS, then R pi, C pi, this voltage is V pi, you have GM V pi, goes to RL, and in addition you have the capacitance to bother about, C mu. Now you have introduced a feedback. In parallel with C mu you have introduced a resistance RF. Okay. What we have to calculate is V0 by IS. So it is a trans impedance or admittance amplifier, trans impedance amplifier, V0 by IS. That is what I have to calculate. Now, in order to analyze this, let us consider some simplifications. Okay, let us consider these two to be combined into a single admittance, and let us call this admittance as Y mu. All right, Y mu obviously is GF plus S C mu. Agreed?
Yes, sir.
Let us consider first, let us combine these two into an admittance of G pi prime. G pi prime would be G pi plus capital GS. Okay, and then we combine these three. We combine these three. No, I must use a different color, black. Let's say we combine along with CPU, C pi, and call this an Y pi admittance. Then Y pi would be G pi prime plus S C pi. Agreed?
Yes.
If I do that, the circuit becomes really simple. Circuit is not too complicated then. What I get is an IS in parallel with an Y pi. I am not using Miller effect. Why not? Because I don't have only C mu, I have a RF also, and I have to be very careful in considering Miller effect. I will do that later, but as long as I can, I will not do it. Okay. Then I have a Y mu. This is V pi, and notice that I have very conveniently ignored Rx. Okay. I have also ignored R01. Why? Because R01 will be very large compared to RL anyway. Okay. And then we have the GM V pi and RL. This is my V0. Now I write two node equations, that is IS equal to V pi Y pi plus V pi minus V0 Y mu. Agreed? And the other node equation is that V pi minus V0 Y mu would be equal to, this current would be equal to GM V pi plus V0 times GL. I am writing in terms of conductances and admittances because the equations remain neat. I don't have to take the reciprocal of anything. If I solve these two equations, very simple, two simultaneous equations, then the transfer impedance ZT, which is V0 by IS, it's a trans impedance amplifier anyway, so the transfer gain has the dimension of an impedance. I show it as ZT. This becomes, if I solve this, it becomes Y pi minus GM divided by GL Y pi plus Y mu times Y pi plus GM. I am omitting this algebraic steps. There is a negative sign here. Obviously, since Y mu is SC mu plus GF, okay, obviously the numerator is a polynomial in S. What degree? First order, first degree polynomial, and therefore the transfer function ZT will have a 0 where? On the negative real axis or positive real axis? Positive real axis. depends on depends on GF minus GM. Which would be greater usually? GM would be greater, and therefore the 0 will be on the positive or negative? Why is GM? Because RF is usually a large resistance. This feedback resistance usually is a large resistance, so GF would be small compared to GM, and therefore the 0 shall be on the positive real axis. Is that clear? I have made a mistake in my calculations, but anyway, we will. No, I have not made a mistake. Now, if I substitute for y mu, y pi, y mu and y pi, obviously I shall get a linear polynomial here, and what will be the order here? 2. So it's a quadratic, linear divided by quadratic polynomial, and by taking the constants out, I can obviously put it in this form. I can put it in the form 1 by c pi. You will see that that comes out as a constant, multiplied by s plus z, that takes care of the 0, and in the denominator I shall have a quadratic polynomial, a polynomial of degree 2, s squared plus b1s plus b0, where the various constants small z, b1 and b0 are as follows. Is this point clear that it will be of this form? Okay. These constants are: small z is GF minus GM divided by C mu. GF minus GM. Okay. Remember, where does it put the 0? Positive real axis or negative real axis? If GF is 0, for example, positive real axis, because the 0 is at s equal to minus z. Is the point clear? Don't be confused on this. Okay, B1 is equal to G pi prime plus GM plus GL divided by C pi plus GF plus GL divided by C mu, and B0 is equal to, there is some algebra which you would do to get this result, plus GF G pi prime plus GM divided by C pi C mu. Okay. Now, in order to find the midband gain, the midband gain obviously shall have the dimension of what dimension? Impedance. So it will be a resistance. Okay. You can show that the midband gain, if you go back to this expression, the midband gain obviously would be 1 by C pi multiplied by, yes, from this expression, Z by D0. That's right. So if you substitute the values and simplify, the midband gain comes out as RT is equal to approximately equal to minus RF divided by 1 plus RL plus RF plus R pi divided by beta 0 RL, where we have ignored, this approximation is valid when G pi is much greater than GS. This is the condition. Otherwise, R pi shall be replaced by the parallel combination of R pi and RS. Okay. This is the situation. Now, is this valid in practice? You have a current generator at the input, and therefore the impedance RS is very high. Okay, so this is a practical situation. Also, if beta is very high, and RL is comparable to RF and R pi, RF plus R pi, then you see that this is approximately equal to minus RF. In other words, the trans impedance basically with a high beta transistor is controlled by that feedback resistance minus RF. This has great significance at a later stage, as you shall see. Before we go, no, wait a second. Let me bring out the significance of this, because this point is very interesting. Suppose your source is not a current source; it's a voltage source. Suppose you have a voltage source, okay? That is, you have Vs and Rs, which can of course be modeled as Is, which is Vs by Rs, and an Rs in parallel. Okay, suppose that is the source. Can you tell me then what would be V0 by Vs? Approximately equal to V0 by Is is minus Rf, and Is is Vs Rs minus Rf divided by Rf. Isn't this very similar to an inverting op amp? Feedback resistance divided by the series resistance Rs. Agreed? I wanted to bring this similarity, that a transistor does behave in under ideal conditions like an op amp. Okay, it's very similar to that of an op amp. That is the gain.
RT is equal to RF won't be valid under this case because GS would be large.
That is right. What I require is Rs much greater than R pi. That's it. If that is satisfied, then this will be satisfied. It's approximate anyway. I just wanted to bring out the similarity. It's an approximate.
How did you get RT similar to minus RF? Can you please elaborate?
How did I get RT is equal to minus RF? You see, if beta 0 is very high, then RL plus RF plus R pi, if these are comparable, approximately let's say 3 RL. So 3 by beta 0. If beta 0 is 300, then 1 by 100. So this term can be ignored. Okay? These are all approximations, they may not be valid in practice. Okay, now let's look at this circuit. What was this circuit? The equivalent circuit. Is, Y pi, Y mu, Gm V pi, some other considerations, and then you had an RL. Okay? Then you had an RL. Now suppose I want to find out the output impedance of this. What do you expect the output impedance to be? Let's call this output impedance as Z0. Output impedance is the impedance faced by RL, the load. So I am not including RL. And for calculation of output impedance, well, this is V pi. What do you do with Is? You take it off. You open circuit this. So we want to find out Z0. How do I do that? I calculate a voltage V here and find out the current I. Is it very difficult? I obviously would be equal to Gm V pi plus V divided by how? So bad. Well, Z pi plus Z mu. Okay.
So we can
I can do that?
GM V pi by a resistance of G1 by GM.
Oh no, this voltage is not V pi. That mistake you must never do. You must check what is the voltage across this. Okay, and you know V pi is equal to what? V times Z pi divided by Z pi plus Z mu. And therefore you can combine this to find out what is I by V or V by I. Agreed? Are the steps clear? The expression that you get is the following. Z out is equal to Z pi plus Z mu divided by 1 plus Gm Z pi. This is the expression that you get. And obviously the midband value R out shall be equal to, what is the midband value of Z pi? R pi prime, where R pi prime is the parallel combination of R pi and RS. Wonderful. Plus RF, midband value of Z mu, divided by 1 plus GM R pi prime, midband value. Now, if R pi is much less than RS, then R pi prime would be approximately equal to R pi, right? And then this becomes approximately equal to 1 by GM beta large beta, beta much greater than 1 by GM plus RF divided by 1 plus beta or beta. So, even though RF is a large quantity, it is divided by beta. Now, what did you expect of R out? Would it be low or high? It is a shunt. What is the characteristic? Both input and output impedance would be decreased. So, this is what it shows. You see, normally from a transistor, the output impedance is of the order of R0. Isn't that right? Whereas this is drastically reduced to a value 1 by GM. Although RF is high, RF is divided by beta. Okay. Let's look at R in, the input impedance. How do you calculate the input impedance? Obviously, you have a Z pi, Z mu, and then you have GM V pi. This is V pi. Now RL shall be there, and at the input you have to connect a voltage source V and find out the current I. In such calculations, I have already pointed this out earlier, that if there is an impedance in parallel with the voltage source, obviously the input impedance Z in shall be equal to Z pi parallel whatever impedance you face here. So, you can take this out of consideration first. First find out what is the impedance here. Instead of writing a equation in which I equal to V by Z pi plus something else, why don't you find out for this one? And this I have calculated earlier. And if you remember, if GM V pi was not there, then it should have been simply Z mu plus RL. If GM V pi is there, the whole thing is divided by 1 plus GM RL. Okay. Once you recognize this, life would be very simple in complicated calculations of high frequency 3 dB cutoff or even low frequency 3 dB cutoff. 1 plus GMRL. And one can show that if beta is much greater than 1 and beta RL is much greater than R pi plus RF, if these are true, then the input resistance, then R in is approximately equal to R pi RF plus RL divided by beta RL. If these two approximations are valid, that is beta much greater than 1 and beta RL much greater than R pi plus RF. Now, take a practical case. RF is, let's say, 10K. GM is 0.04 moles. What is the collector current? Oh, no, it should be here. 1 million. 1 by 25 is 0.04. Okay. Beta is 50. It's not a very good transistor. And RL is 1K. Then you can show that R out, the mid-band value of the output resistance, is equal to simply 225 ohms. It's a low value. And R in is equal to 235 ohms for this set of values. The input impedance is also low. What is R pi? 50 divided by 0.04, that means how much? 50 multiplied by 1.25 K. You see, it has been brought drastically reduced to 235 ohms. I want you to appreciate this, that a shunt, although it's obvious, reduces the input impedance and also the output impedance, because this will be used later to make an overall amplifier in which shunt would be cascaded to, can you guess what kind of a second stage I can cascade to without much of a problem? No, I want again a local feedback circuit. Shunt, whom should I couple to? Shunt series? No. Input must be series, because my output impedance is low. I must connect to a stage whose input impedance is high. Common collector is fine. Common collector is a series. Yes. What is the output circuit? Common collector, emitter, follower. What kind of feedback? Series? Are you sure? Series or series shunt? Series shunt, because the total output voltage is being fed back. It's a voltage component. Don't make a mistake, because then in the A circuit and beta circuit you will make mistake. So I repeat, the shunt circuit that we saw today is ideal for cascading to a circuit whose input is a series comparison. We don't care what the output is. Series comparison, for example, a series circuit would do. Okay. Next time, in the next lecture, we will bother about the $1 million question of FH, how to calculate FH for this. Okay.